Okay, we're going to look at other indeterminate type of questions um, that we are eventually going to use L'Hopital's rule to prove what the limit is, but we had to first get it into L'Hopital's form. First one is something like 0 times infinity. So 0 times infinity, you may want to say the answer is just 0. A lot of times it is, but we cannot just actually assume that a number 0, which is basically saying nothing, multiplied by a very, very large number, we'll just get rid of it. We need to mathematically prove that by L'Hopital's rule. L'Hopital's rule means you have a ratio of 2 limit that, so what we want to prove is that by ratio of 2 limit, that ratio eventually does go to 0, or maybe it doesn't, it goes to another number. We don't know, but we want to actually prove that. So for example, this first one, if you plug in 0 from the plus side, this is in this function, it's going to go to 0. In this function, it's going to go negative infinity. So then this is 0 times infinity. We cannot use L'Hopital's rule because it is not in the L'Hopital's rule indeterminate form. So we want to get it into a 0 over 0 form or a infinity over infinity form. So this is going to be limit as x goes to 0 plus. And what we want to do is make it look like infinity over infinity or 0 over 0. I'm going to actually make it look like infinity over infinity. So it's going to be natural log x over 1 over x. That way, natural log x goes to infinity when x is 0. And then 1 over x goes to infinity when x is 0. So to use the L'Hopital's rule, we need to prove that we can. So this is going to infinity, or actually negative infinity, sorry about that. And then a limit as x goes to 0 plus 1 over x is going to infinity. So we're going to use L'Hopital's rule. And then we're going to take the derivative of the numerator, derivative of the denominator. So if you plug in 0 at this time, you're still going to get infinity over infinity, which is not what we want to do. We want to simplify this so that we achieve our goal. If you just plug in as is, you're going to basically do L'Hopital's rule for a very, very long time, which is not preferred. All right, cancel that. You get limit as x goes to 0 plus of negative x. This is equal to 0. So we proved by L'Hopital's rule, making this limit as if it's a comparison between two ratios. A ratio comparing two functions. This is actually going to 0. Okay, let's look at this example. When x is going to infinity, so this function is going to infinity. This function, well, that's going to be e to the negative infinity squared, which is 1 over e to the infinity squared. That is 1 over infinity, which is going to be 0. So we have a case of infinity times 0 again. And we want to make it look like the L'Hopital's form of indeterminate form. So this one is actually easily done by just changing this to where it really ought to be. This negative exponent, put it into where it ought to be. X cubed over e to the x squared. Okay, now if you mentally plug it in, you'll see that you're going to get infinity over infinity, which is the form we want. So let's prove that we can use L'Hopital's rule. Okay, so that is infinity over infinity. We're going to use L'Hopital. Okay, so this is going to be limit as x goes to infinity 3x squared over e to the x squared times 2x. Limit as x goes to infinity 3x over 2e to the x squared. Okay, let's plug in infinity right now. And we're still going to get infinity over infinity, which means we gotta use L'Hopital one more time. Let's prove that we can use L'Hopital's rule. Limit as x goes to infinity of 3 over 2e to the x squared times 2x. All right, simplify that. Limit as x goes to infinity of 3 over 4x e to the x squared. Okay, so if you plug in infinity right now, you're going to get 3 over infinity. And in this case, that is 0. So we did prove that it is 0. Type 2. Type 2 is the case where you have infinity minus infinity. This is where you may be tempted to say that the answer is 0. However, we cannot prove that it is 0 because when you say infinity, you're talking about infinity minus infinity. You're talking about, remember what infinity really means. Infinity means expanding out of bound, meaning it's so big that it cannot be contained. So you have two numbers that cannot be contained and you're subtracting each other. You cannot say that they're actually the same size. Remember to have a number subtracting a number to get 0. They have to be exactly the same size. You have two things that's very, very large so large that we just use infinity to represent them. We cannot say that they are actually the same size. So we can't, precisely say that it is actually 0. So we need to actually prove using L'Hopital's rule. And what L'Hopital's rule does is it forces the function to look like a ratio of two functions so that we can just look at how big one is compared to the other in terms of proportion. So to make them actually a ratio of each other, I can't really think of a clever way to do this, so I'm going to just combine them into one big function. So that means multiply this function on the left with x minus 1, the function on the right with natural log x, and then combine the two denominators. Okay, now let's look at plugging in 1. Okay, so in the numerator, 1 minus 1 minus natural log 1. Natural log 1 is 0, and the whole thing just becomes 0. Okay, in the denominator, natural log 1 is 0, x minus 1, so 1 minus 1 is also 0. So it's going to be 0 over 0, which is what we want. So let's prove that we can use L'Hopital's rule. All right, L'Hopital's rule. All right, taking the derivative. 1 minus 1 over x over natural log x times 1 plus x minus 1 times 1 over x. Okay, let's try to simplify it and see what we get. X minus 1 over x over x natural log x plus x minus 1 over x. Okay, let's simplify this some more. Limit as x goes to 1 plus x minus 1 over x times x over x natural log x plus x minus 1. Limit as x goes to 1 plus x minus 1 over x natural log x plus x minus 1. All right, let's see what happens if we plug in 1. we get 0 over 0 again. That tells me that we need to take L'Hopital's rule one more time. Okay, so let's prove that we can use it. X is going to 1 plus of x minus 1, that's equal to 0. Limit as x goes to 1 plus x natural log x plus x minus 1 is 0. So we're going to take L'Hopital's rule. I'm going to go up here. Okay, the derivative of the top. Get 1. Derivative of the bottom, x natural log x means product rule, so x times 1 over x plus natural log x plus 1. Okay, that's gonna cancel. So limit as x goes to 1 plus of 1 over 1 plus natural log x plus 1. Put in 1, we get 1/2. So this limit, even though it looked like it was infinity minus infinity at the time, actually that limit is going to 1/2. So if we just assume that it was 0, it would not be correct. Okay, let's practice another one. If we plug in 0 right now, we're going to get infinity here. And this one, e to the 0 is 0. Sorry, e to the 0 is 1. 1 minus 1 is 0. So we're going to get the infinity minus infinity again. So again, what we want to do is make it into a L'Hopital's rule form. All right, and then let's check again. All right, if we put in 0 plus, we get 0 on the top and 0 on the bottom. Okay, so this is going to be L'Hopital's rule. Okay, L'Hopital. Limit as x goes to 0 plus, the numerator, derivative of the numerator is e to the x minus 1 over product rule, x times e to the x plus e to the x minus 1. Okay, plug in 0, you get 0 on the top. On the bottom, you still get 0. Let me double check. I don't think we can cancel anything. Okay, so we're kind of stuck as it is. So let's go ahead and do L'Hopital one more time. Okay, limit as x goes to 0 plus, in the numerator you get e to the x. In the denominator you get x e to the x plus e to the x, that's the product rule, plus e to the x, and the derivative of minus 1 is 0. All right, plug in 0. We get 1 over 0 plus 1 plus 1, 1/2 again. So this limit is actually going to 1/2. Now type 3 is where we get something like this. 0 to 0, infinity to 0, or 1 to infinity. Now 0 to 0, we cannot conclude that it is just going to be 1. Not everything going to raise to the 0 is 1, especially if we're talking about limit, because limit is actually not a number per se. because we're saying it's tending to go to this number. It's not a definite number. So then when something is tending to go somewhere else or to go somewhere and that is raised to a 0, we can't just conclude that it's going to go to 1. And same thing here. This 1 is not an actual number 1. It is a limit 1. So if you're saying, like, if you multiply 1 by itself to the infinite power, is it going to be 1? Of course, it's going to be 1. But we're not talking about a absolute number 1, meaning it's not a number 1. It's just saying this limit is tending to go to 1. This function is trying to go to 1, but it's never actually at 1. So then you can't just say that it is always going to be 1. Okay. So again, when you get to any of this kind of situation, you want to try to get to a L'Hopital thing. So let's look at this question. If you plug in 0 right now, you're going to get 0. No, you're going to get to 1 to the infinity. This tells us that we can't quite conclude what is really going to happen. So what we want to do is try to get to L'Hopital's rule, but there is not any good way to get it into L'Hopital's rule because we can't really have a ratio of something over something because this function is in the exponent. So recall, the only way we know to get a exponent down into kind of the normal numerator area is to use natural log or some kind of log. So I'm going to just say that this function is equal to 1 minus 5x to the 3 over x. And then what I'm going to do is take natural log of both sides. That way I can get the exponent down. You just need to remember that you did take natural log of both sides. So you did change this function. So then when you're finding the limit, you're not actually finding the limit of the original function. You need to go back and fix that number later once you do have the limit. Okay, so let's take a look at this now. If you plug in the limit, so let's say we are trying to find the limit again. So limit as x goes to 0 of, now we're going to take the limit of both sides. So this is going to be limit of f of x equals to limit as x goes to 0 of 3 over x natural log 1 minus 5x. I'm going to change that a little bit. Limit as x goes to 0 of 3 natural log 1 minus 5x over x. If you plug in 0 right now, you're going to get 0 over 0. Okay, so we can use L'Hopital's rule. So let's prove that we can. Limit as x goes to 0 of 3 natural log 1 minus 5x is equal to 0. And then limit as x goes to 0 of x is going to 0. So L'Hopital's. So the derivative of the numerator is going to be 3 times 1 over 1 minus 5x times negative 5. Derivative of the denominator is 1. Okay, simplifying that a little bit. Limit as x goes to 0 of negative 15 over 1 minus 5x. Plugging in 0, you're going to get negative 15. So the limit looks like it's going to negative 15. However, if you recall, this is not actually the function. This is the limit as x goes to 0 of natural log of the function. So what we want to do as the last step is just raise both sides by e, because we are trying to find the limit as x goes to 0 of the function, not the natural log of the function. Okay, this next question is the same. So you're going to plug in infinity right now. You're going to get infinity to 0. Infinity to 0. And that tells us that we have to use something to prove that it is going to a number, or maybe it goes to infinity. So just like the previous question, we're going to set the function equal to f of x. And we're going to take natural log of both sides so we can bring down the exponent. Natural log f of x is equal to e to the negative x natural log x. So let's take the limit on both sides. Limit as x goes to infinity of natural log f of x is equal to limit as x goes to infinity of e to the negative x. Oh, let's just change it to this. All right, now let's plug in infinity. You're going to see that it is, again, a situation where we can use L'Hopital's rule. Okay, so use L'Hopital's rule. Take the derivative. 1 over x over e to the x. Okay, simplify that. Limit as x goes to infinity of 1 over x e to the x. This is going to be 0. So again, this is equal to the limit as x goes to infinity. Infinity of natural log of the function. So the last thing we want to do is just raise by e, and this is going to be limit as x goes to infinity of f of x is equal to 1. All right, one more here. Why don't you give this one a try on your own? This is 0 to the 0, so you have to prove whatever that limit is the correct limit. So again, you're going to use L'Hopital's rule, but first set it equal to a function, take the natural log of both sides to get that x down. So pause the video and then come back and check your answer. Okay, so hopefully you did the same work and you got to this point. Okay, so if you wanted to take a look, you can pause the video and look at this, the work to compare to yours. So again, you get to this point. This is not the end. This is the limit as x goes to 0 plus of natural log f of x, which is equal to 0. So the last thing we want to do is just raise both sides by e. So we get limit as x goes to 0 plus f of x is equal to 1. Now, 1 to the infinity, is that equal to 1? Okay, we're going to do the same thing here. Okay, if you plug in 0 here, you're going to get sine 4 times 0. Sine 0 is 0 plus 1, that's 1. Cotangent of 0, so let's kind of think about cotangent. Cotangent x is equal to cosine over sine. So cosine of 0 is 1. Sine of 0 is 0. So 1 over 0 is going to get us infinity, or just it's just a very, very large number. So this is going to be 1 to infinity. And again, we cannot solve it as is, so we need to force it into a L'Hopital's rule form. Okay, so we have another case of the variable in the exponent. So we're going to do this, bring that down. Okay, then we are going to apply limit. Let's double check what we're going to get. So cotangent x, we said that is going to infinity. Natural log 1 plus sine 4x, we said that was 0. So 0 times infinity. All right. Let's just change it a little bit. Cotangent is the same thing as 1 over tangent. So we can write it this way. Let's double check. Okay, so now if I plug in 0, I'm going to get 0 in the numerator. Tangent 0 is 0. So this is 0 over 0, which is what we want. So let's write out our proof for L'Hopital's rule. Okay, use L'Hopital and then take the derivative of numerator and denominator. Numerator is 1 over 1 plus sine 4x times chain rule. Cosine 4x times 4. Denominator secant squared. Okay, let's plug in 0 and see what we get. Does not look like we're going to get a undefined situation again, so that's good. I'm going to just simplify this so it's easier to look at. 4 cosine 4x over 1 plus sine 4x, and then that secant squared is a denominator, so it kind of comes together. Plug in 0. Cosine 4 times 0 is 1, so that's 4. In the denominator, 1 plus sine times sine 0 is 1. Secant square of 0, that's 1 over cosine square of 0. Cosine of 0 is 1, so that's just 1. So that is 4. Okay, last step. 4 is equal to limit as x goes to 0 plus of natural log f of x. I'm going to raise both sides by e. So limit as x goes to 0 plus of f of x is equal to e to the fourth.